So let's say you're part of a planning team for a small college or university, and you've been tasked with laying a new network of cables between all of the buildings in one part of the campus. Now, you've got a map of the buildings that you can connect and implicitly the ones that you can't, or for whatever reason. And your goal is to pick the buildings to connect in such a way that first you have the minimum number of connections, and second, every building can be reached from every other building. Right? This arrangement is what's called a spanning tree of the original graph. Now, we can take this a step further by adding weights to the graph. Right? These might be pure physical distances, or they might be calculated from some metric that takes into account things like the difficulty of getting between two of the buildings. Now we want not just the spanning tree, but the so-called minimum spanning tree. That is the spanning tree that has the smallest total weight. So before we go any further, let's take a look at some examples here. This tree, for example, would be a spanning tree for our map from the previous slide. Specifically, it's a spanning tree with, if you add up all the numbers, a total weight of 777. This graph, on the other hand, would also be a spanning tree, but this time with a total weight of 718. So, looking at these graphs begs kind of an obvious question. How can we go about finding the minimum spanning tree given just kind of an arbitrary network? Now, that's the obvious question for an engineer to ask, but a mathematician, his obvious question would start a step further back with an even more fundamental one. Can we be sure that for a given graph, it has to even have a spanning tree? Okay, so it turns out the answer to that question is yes, and that's the first sentence in our theorem here. But also, there's a second part to this that's kind of interesting. Every spanning tree of a graph is going to have the same number of edges, right, regardless of how we construct it from the original. So proving these both is pretty straightforward. Every connected graph has a spanning tree. Well, let G be a random graph. If the graph has no circuits, then it's a tree, and essentially it's its own spanning tree. If the graph does have a circuit, break it. Right? Just remove an edge from it. Remember, we saw a theorem a few lectures back that said if a connected graph has a circuit and you take an edge out of that circuit, the graph is still connected. Right? So I'm not going to break my graph by breaking the circuit. So our new graph, if it has no circuits, if there's only one in the original, then our new graph is a tree. That's the spanning tree, and we're done. If it does have a circuit, just keep doing this. Right? Keep removing an edge from every circuit until we get to a graph, that doesn't have any more circuits. That graph is the tree that we're looking for. To say that every spanning tree of a graph has the same number of edges, this is also pretty straightforward. Suppose our original graph has v vertices. Then every spanning tree is going to have v vertices because the vertices we aren't allowed to change. We can take away edges, not the vertices. Right? So if every spanning tree has v vertices, then another theorem that we saw earlier, every spanning tree must have v minus 1 edges. In other words, it has to have the same number. Okay, so now that we've gotten those preliminaries out of the way, right? We know what trees are, we know what weighted trees are, and we've gotten past this question of existence. We know every graph is going to have a spanning tree. In the next couple of lectures, we're going to take up the question of how we can find not just a spanning tree, but the minimum spanning tree.